Alright guys, in this video we're talking about 3.3 expected values. Before talking about the definition of expected values, I would like to start with an example. So what I will give you here is a frequency distribution. Let's say x. I'm sorry. Let me pull out the markers. So what we will do here is I will give you the frequency table. So x and the frequency. So the values of x could be 1, 2, 3, 4, and 5. And the frequency of each of them are 3. The frequency of 1 is 3, frequency of 2 is 2, and the frequency of 3 is 4, and the frequency of 4 is 6, the frequency of 5 is 8. And let's call those x values are x1, x2, x3, x4, and x5. And I want to find x bar. So I want to find the average value of of x. So what we want to do here is that if we want to find the average value of x, we want to add all the possible values of x together and divide it by the total frequency. So first of all, let's take a look at what's the total frequency over here. The n would be equal to the sum of all the values of frequency over here. So the 5 plus 4, 9, and plus 14, which is 23. And then we just need to go ahead and apply the formula of the average, so which is each possible value multiplied by the frequency. So 1 times 3, because we got 3 ones in the frequency table, and then plus 2 times 2, and then plus 3 times 4, plus the value of 4 times its frequency, which is 6, and then plus 5 times 8. And then divided by the total frequency, which is 23. And then what I'm doing next is I will break it into 5 different parts. So this would be equal to 1 times 3 over 23. I can do that, right? Plus 2 times 2 over 23, plus 3 times 4 over 23, plus 4 times 6 over 23, plus 5 times 8 over 23. So what I'm doing here, I just break this fraction into 5 parts and into a summation of 5 different parts, and I will drop the x value and keep the frequency of the corresponding x value on the top of the fraction. So what I'm gonna do next is, we know that 1 is the value of x, which is x1, right? x1 times, no, we have 3 over 23 over here. What is 3? 3 is the frequency of x1, and the 23 is the total frequency. The frequency divided by the total frequency will give us the probability of x1. So this is the probability of x1. And then plus 2 is x2 times 2, this 2 on the top here is the frequency of x2, and 23 is the total. So frequency divided by total is the probability of x2, right? P of x2. And then plus 3 is x3 times 4 is the frequency of x3. So the frequency divided by total is probability of x3, and so forth, plus x4 times probability of x4, plus x5 times the probability of x5. And then if I want to put this whole thing in a form of summation, it's gonna be sum of I is that would be I is equal to 1 through 5 sum of xi times the probability of xi. So basically, the average is equal to the sum of the multiplications of each x value and its corresponding probability. And this brings us to the definition of expected values. So definition, let x be a discrete random variable with set of possible values d and PMF P of x. So the expected value or mean value of x denoted by e of x or mu sub x or just mu. So you can use e of x or mu sub x or mu. Is mu is equal to e of x is equal to mu sub x is equal to the sum of the each x value multiplied by its corresponding probability. Okay, and the notation expected value and mean value are completely equivalent. So I think this part is quite straightforward, and this form here, this formula here is derived from the formula of the average, which we went over in chapter 1, I guess. So if this is clear, let's take a look at example. So I will give you a probability distribution over here. So x, the possible of x values are 0, 1, 2, 3, and 4. And then the probabilities are, the probability x is equal to 0 is 0.2. The probability that x is equal to 1 is 0.1, and then 0.15, and then 0.3, and then 0.25. So I want you to find, of course, this is a probability distribution. So we want to find out the expected value e of x. So if we have the probability distribution and we want to find out the expected values, what we need to do, just apply this formula over here. That would be equal to the sum of each x value multiplied by its corresponding probability. So that would be 0 times 0.2 plus 1 times 0.1 plus 2 times 0.15 plus 3 times 0.3 plus 4 times 0.25. Okay, and of course 0 times 0.2 is 0 plus 1 times 0.1 is 0.1 plus 2 times 0.15 is 0.3 plus 3 times 0.3 is 0.9 plus 4 times 0.25 is 1. So this would be equal to 2.3. And that's how we find the expected value given the probability distribution. I think once you know the formula over here, that's pretty straightforward. Okay, so once this is clear, let's take a look at another example, which is very similar to the one we just went over. So this is coming from the textbook, example 3.17, and the background information is given here, and I don't want to read it over, but we know that let x be the Apgar score of randomly selected child born at a certain hospital during the next year, and suppose that the PMF of x. So we have the probability distribution of x, which means we know the possible values of x. It could be 0, 1, 2, 3 until 10. And the probability of each x value is 0.002, 0.001 until 0.01. And we want to find the mean value of x. So in other words, we're looking for the expected value. So just keep the idea in your mind. The expected value and the mean value are completely equivalent to each other. So if we want to find the expected value, we know all of the possible x values or the possible values of x, and we know the probability of each possible x value. So what we need to do, just apply the formula in the definition here. So that would be equal to the summation of each x value multiplied by its corresponding probability. So over here it's going to be 0 times 0.001 plus 1 times 0.002 plus 2 times 0.002 and so forth until 8 times 0.25 plus 9 times 0.12 plus 10 times 0.01. And then you add them all up, type it in your calculator, you'll find the answer, which is 7.15. And that's how we'll find the expected value in this case. Okay, next one. This is another example 3.20 from the textbook. Let x, the number of interviews a student has prior to getting a job, have PMF. So we have P of x is equal to k over x squared. Of course, x could be and any integers greater than or equal to 1. So 1, 2, 3, and so forth, and 0 otherwise. Or k is chosen so that the sum from x is equal to 1 to infinity, k over x squared is equal to 1. So why do we have that? Why do we have sum x is equal to 1 to infinity, k over x squared is equal to 1? So this is one of the important properties of PMF, as what we went over previously in the previous video. I mean, the sum of the PMFs, or the sum of all possible the sum of all probabilities is equal to 1. The sum of all probabilities of a discrete random variable is equal to 1. Okay, that's what we have here. In a mathematics course on infinite series, it is shown that the sum of from x is equal to 1 to infinity, 1 over x squared is finite or less than infinity. So I don't want to prove over here, and I think you might have say something like this in your calculus class. So which implies that such a k exists, but its exact value need not concern us. So basically, we don't have to worry about the exact expected value in this case. What we need to know is how to find the expected value by applying the formula given in the definition here. So basically, what we need to do is that we know that mu is equal to e of x is equal to the sum of x times p of x, right? So of course, x in the simple space D. And of course, in this case, x could be any number from 1 to infinity, and times x times p of x. And we know the p of x is equal to k over x squared, right? So this would be equal to, since k is constant, we can factor out of the summation. It's going to be k times sum of x from 1 to infinity. And since this will cancel out the square over here, then we have 1 over x. So this part is the harmonic theory, but we don't have to worry about that in this case. What we need to do is how to find this by applying the definition of expected values. Okay, I think what we just went over was pretty straightforward. So once we know how to find the expected values directly, let's take a look at how to find the expected values of a function. So once again, every time if you want to find an expected value, whatever is expected value of a random variable or the expected value of a function, what you want to think of at the first is this formula over here. E of x is equal to the sum of x times the probability of x. So you want to think of this formula. So once we take a look at it, this formula here, if we want to find the expected value, what do we need? We need the possible values, and we need the probability of each possible value. Okay? Once we figure out both of them, we just need to add the multiplication of each pair together. That's what we need to do. Okay? Once this is clear, let's take a look at this example here. I will give you a probability distribution of x. So the possible values of x are 4, 6, and 8. And then the probability of each of x value is 0.5, 0.3, and 0.2. Okay, now I gave you that y is equal to h of x is equal to 2x plus 1. Okay? And we want to find the expected value of y. Okay. Now, based on what I said previously, we know that if we want to find the expected value of y, first of all, we want to find all of the possible values of y, right? So based on the relationship we have over here, we know that the value of y depends on the value of x. So first of all, we need to find the values of y first. So of course, what we need to do, just plug each x value back into this relationship over here. Let's say y1 is equal to hx1, which is 2 times 4 plus 1, which is 9. And then y2, we plug the second x value back into the relationship, 2 times 6 plus 1, which is 13. And then y3 is equal to h of x3 is equal to 2 times 8 plus 1, which is 17. Okay, now we have all the possible values of y's. And of course, we can tell from based on what we get over here, we can tell that the probability of y1 is going to be equal to the probability x is equal to 4, which is 0.5. Okay, and the probability of y2 is going to be equal to the probability that x is equal to 6, which is 0.3. And the probability of y3 is going to be equal to the probability x is equal to 8, which is 0.2. Now, once we know that, we can build up the probability distribution for y. Let's do y and a p of y. So the possible values of y are 9, 13, 17. And the probability of each of them would be 0.5, 0.3, and 0.2. Okay? Now, if we want to find the expected value of y, so that would be equal to the possible value of y multiplied by is probability. So it's going to be 9 times 0.5 plus 13 times 0.3 plus 17 times 0.2. And this would be equal to 4.5 plus 3.9 plus 3.4, I mean. So if we add them all up, this is 11.8. Okay? And actually, we can derive the formula that E of y, of course, is going to be equal to the sum of that y is equal to the sample space of y, all the possible values of y times p of y. And this is going to be equivalent to, since we have that y is equal to h of x, right? So E of y would be equal to E of h of x, which is equal to the sum of h of x times p of x for x in the belongs to all the possible values of x, d. So what we're doing here, we are translating the y into the form of x, because we know based on the probability distribution given here, we know the probabilities of each x value. Now we can apply this formula because we cannot get the probability of y's directly. Okay. All right, so once this is clear, let's take a look at this proposition over here. If the random variable x has a set of possible values d and p of x, then the expected value of any function h of x denoted by e of h of x or mu sub h of x is computed by e of h of x is equal to sum of each value of h of x multiplied by its probability. As this is exactly the same thing as what we just went over here. Okay. Now, once we know this proposition, let's take a look at the rules of expected value. The function h of x of interest is quite frequently a linear function, ax plus b. In this case, e of h of x is easily computed from e of x. Okay, so the e of ax plus b is equal to a times e of x plus b. Now let's take a look at the proof. Let's take a look at how we got this equation over here. So before talking about the proof, I just want to let you know that in chapter 3, we're talking about the probability distributions of a discrete random variable, and in chapter 4, we're going to talk about the probability distribution of continuous random variables. So they are actually, sort of similar. So the main difference between chapter 3 and chapter 4 is that obviously in chapter 3 we're doing the summation to find out the expected values. We do the summation, and in chapter 4 we're gonna do the integration. That's the main difference. So I will go over all the proofs in chapter 3, and then I wouldn't do that again in chapter 4 because they're very similar. So the only difference is just you just need to change the summation to integration. Then you will find the expected values of continuous random variable. So in chapter 4. So we're gonna talk a little bit more about that in the future. So I just want to let you know that I'm going to go over the proofs in that section, but I wouldn't do it again in the future. Now, let's take a look at how do we get this. So if we want to prove this proposition, we got to go back to the definition, okay? Now, we know that E of AX plus B. So that would be equal to the sum of X in D. These are the possible values of X times AX, we don't need the parentheses over here, AX plus B times P of X. This is coming from the proposition we just went over here. Of course, in this case, H of X is equal to AX plus B, okay? And then what I'm doing next is I want to distribute this P of X into the parentheses here. So that would be equal to the sum of X in D and then AX times P of X and then plus B times P of X. Okay, we can do that, right? And then I will break it into two parts because we got a sum over here. So that would be equal to the sum of X in D and then AX times P of X, and then plus the sum of X in D, B times P of X, okay? Now, since both A and B are constant numbers, and it wouldn't affect the summation, so I'm gonna factor them out of the summation, so that would be equal to A times sum of X in D, X times P of X. And then plus B times the sum of X in D, P of X. Now, what is this? What is sum of X times P of X? That's the expected value. So this would be equal to A times E of X. Plus, what is the sum of all probabilities? The sum of all probabilities is going to be equal to 1. So this would be B times 1, which just B. So the expected value of AX plus B is just equal to A times the expected value of X and then plus B. And that's why. That's how we got this equation over here. Okay, once this is clear, so there are two special cases. So which are for any constant A, if B is equal to 0, then the E of AX is going to be equal to A times E of X. So of course, if B is equal to 0, this part is gone. So that would be equal to A of X directly. And if A is equal to 1, so E of X plus B is going to be equal to E of X plus B. So of course, if A is 1, so this part is just 1. Okay? Okay, so once this is clear, let's take a look at an example. And we have already known that, let's go back to the previous example. So we have that X is 4, 6, and 8, and the probabilities are, let me clean the screen for quick because it doesn't work well again. The probabilities are P of X are 0.5, 0.3, and 0.2. Of course, this is the exactly same thing as the previous example, and we want to find the expected value of 2x plus 1. So based on the formula, the proposition we just went over, we know that the expected value of 2x plus 1 is going to be equal to the 2 times e of x plus 1. So if we want to figure out this, we just need to find out the expected value of x and then plug it back into here. We'll figure out the expected value of 2x plus 1. Now let's take a look how to find e of x. So based on the definition, that would be equal to the sum of the multiplications of each x value times its corresponding probability. So that would be 2 times 0.5 plus 6 times 0.3 plus 8 times 0.2. Okay, so that would be equal to 2 plus 1.8 plus 1.6, right? So that would be 5.4. So once we have e of x is a 5.4, so we plug it back into here, we're going to have 2 times 5.4 plus 1. So which is equal to 11.8, which is exactly same thing as what we got up here. Where is it? It's over here. Exactly same thing, okay? And I believe this part, and this way we went over down here is quite easier than the previous way we just went over, because in this case we don't have to find out all the y values first. What we need to do is just find out the expected of x and then plug it back into this formula. So I think this proposition is very important, and once you are familiar with this, it's gonna save you a lot of time. All right. After the expected values, let's take a look at the variance. First of all, the definition. Let x have PMF P of x and expected value mu. The variance of x denoted by V of x or sigma x squared or just sigma squared is equal to the sum of, for all of the x values, for x in all the possible values of x, the sum of x minus mu squared times P of x, which is equal to e of x minus mu squared. And of course, the standard deviation of x is equal to the square of variance. Now let's take a look at how do we get the formula, those two formulas over here. And we know that based on what we went over in the very first chapter, based on the definition of variance, we know that the variance is equal to the sum of all deviations about the population mean, the square deviations about population mean divided by total frequency, okay, capital N. And then what I'm doing here, let me rewrite this. So what I'm doing here, I will set yi is equal to, no, let me rewrite it over here. Let me see how to rewrite it. Okay, just rewrite it over here. Ya is equal to sum of xi, not sum. We don't need the summation part. So we want yi is equal to xi minus mu squared. So we just do the substitution over here. Then this part, the top part would be, since the xi minus mu squared is equal to yi, so over here we're going to have sum of yi over n. Sum of yi over n, this would be equal to the expected value of y, right? Of course, this is completely equivalent to each other, that sum of xi minus mu squared over n. Let me rewrite this, since obviously the screen doesn't work well again. Square and n. And this would be equal to e of x minus mu squared. So the reason why those two are equivalent is because we set yi is equal to xi minus mu squared. That's why. Okay. All right. Of course, based on the definition of expected value, the e of something here, that would be equal to, we know that e of x. Clean it. I don't know why it doesn't work well again. E of x is equal to sum of x times p of x, and we know that e of h of x is equal to the sum of h of x times p of x. So what do we have inside here is x minus mu squared. If we consider this x minus mu squared as h of x, so this would be equal to sum of x minus mu squared times p of x. Okay, so which is exactly the same thing as what we got here. So the reason why I'm writing here, I'm explaining how do we get those two expressions from the definition of variance. Okay. Now, once we know that the formula or the definition of a variance, let's take a look at an example. Let's take a look at an example down here. The probability distribution of x is given here. So the possible values of x could be 1, 2, 3, 4, 5, and 6, and the probability of each x value is 0.3, 0.25, 0.15, 0.5, 0.10, and 0.15. So we already have that mu is equal to 2.85. Of course, we can calculate it by ourselves by applying that mu is equal to the expected. E of x is equal to the sum of x times p of x. Okay, let me clean the screen. So of course, in this case, so it's going to be equal to 1 times 0.3 plus 2 times 0.25 plus 3 times 0.15 plus 4 times 0.05 plus 5 times 0.10 plus 6 times 0.15. And then if you add them all up, this would be equal to 2.85. Okay? And then we want to find a variance. So if we want to find a variance, we just need to apply the formula that variance is equal to the expected value of x minus mu squared. And this is equal to sum of x minus mu squared times p of x. Okay. So, and what we know that the value of mu is 2.85, so we get 2.85 here, and then we just need to plug each x value and the probability back into here. So that would be equal to x1 1 minus 2.85 and then squared multiplied by 0.30, and then plus x2 2 minus 2.85 squared and then times 0.25, and until the very last x value 6 minus the mu 2.85 squared, and then multiply by its probability 0.15, and you will get this is equal to 3.2275. Okay, if you type the whole thing in your calculator. And of course, the standard deviation would be equal to the square root of the variance, which is equal to square root of 3.2275, which is equal to 1.8. And I think this part, actually the calculation is kind of long, but there is nothing hard to think of. Once you know the formula or the definition of variance, it's just, and you know how to find the expected values, and then it's just a plug and play. There's nothing hard to think of. Okay. So actually, If you want to find out, if you want to calculate the variance of a random variable, of course you can apply the definition as what we just went over up here, or you can apply the proposition given here. The variance of x is equal to the e of x squared minus the quantity squared of expected value. Now let's take a look at the proof here. So based on the definition, we know that the variance of x is equal to sum of x out of the possible values, and then x minus mu square. Let me rewrite this part. Times p of x. Let me rewrite this part because it doesn't look good. P of x. And then what I'm doing next, I wanna, and of course over here the mu is always constant. Mu is constant. I don't know why this doesn't work well. It's constant, okay? It's constant. Mu is a constant number. It doesn't change when the x values changes, because once the population or the data set given, the mu is always constant. So what I'm doing here, I want to apply the formula of perfect square. I want to spread out this part over here. X in d, and then it's going to be x squared minus 2 mu x minus mu square times p probability of x. And then I want to distribute this p of x into the parentheses. So it's going to be equal to the sum x in d, then x squared times p of x. Actually, we can break it into 3 parts. Let me just I'm gonna skip a step. X squared times p of x minus sum of 2 mu x p of x, and then minus the third part. I think this is a plus the sum of mu square. This part. Mu square p of x. And then, of course, based on the definition of e, the expected value, the sum of x squared times p of x, this is going to be equal to e of x squared, right? This is e of x squared. And then this minus, since mu, both mu and 2 are constant numbers, we factor it out of the summation. So that will be 2 mu times the sum of x p of x. And then plus, we factor out this mu squared sum of p of x. So this is equal to e of x squared minus the sum of x times the probability of x is the e of x. This part is just mu, right? Or e of x, same thing. So 2 mu squared because 2 mu times mu is 2 mu squared. So we get 2 mu squared over here. And then plus, since the sum of all probabilities is equal to 1, so mu squared times 1 is mu squared. And then this is going to be equal to minus 2 mu squared plus mu squared, just minus mu squared. So E of x squared minus mu squared. And we know that mu squared is just the quantity square of the expected value. E of x squared minus E of x quantity square. So this is the exactly same thing as what do we get over here? As what do we get over E of x squared minus the quantity square of the expected value, okay? And this is a proof here how we got this proposition. Actually, once we know this proposition over here, it's gonna save us a lot of time. Let's take a look at an example. So in the previous example here, let's take a look at how to calculate the variance in the previous example here by applying the proposition we just went over. So in this case, we have already known the expected value is 2.85, right? And we just need to find E of x is equal to, well, let's just take a look at it here because it's I don't know why it's just hard to write down. And I don't know why this keeps happening. So we know based on the proposition we went over here, the variance of x is equal to E of x squared minus the quantity square of expected value. And in this case, we have already the expected value, which is 2.85. In other words, if we can find the E of x squared, we just need to plug both of them back into here to find the variance. Okay? Now let's, we know that, we know that the expected value is equal to 2.85. And then we want to find E of x squared. E of x squared. And based on the definition, this would be equal to sum of x squared times the probability of each of x. And then we know the possible values of x could be 1, 2, 3, 4, and 5, 6. So that would be 1 squared times the probability of 1, which is 0.3. Plus 2 squared times its probability, which is 0.25, as given in the in the previous example, and then plus 3 squared. Oh, let me write this. 3 squared times its probability, which is 0.15. And then plus 4 squared times its probability 0.05. And then plus 5 squared. What is doing here? Give me 1 second. This would be, oh, I see why. 5 squared times is 0.1 plus 6 squared, and then times is 0.15. Okay? And then we just type the whole thing in your calculator. You'll get this thing is equal to 11.35. And then the variance in this case would be equal to e of x squared minus e of x quantity squared. So which is equal to e of x squared is 11.35, and then minus, we know the e of x is 2.85 minus 2.85 squared. And this gave us 3.2275 if you type it in the calculator. So of course this is exactly the same as what we got I think over here, which is exactly the same thing as what we got over here. So either way would work, and I will encourage you to apply the proposition over here because you get less calculation to do. Of course, you can figure it out by applying the definition, but it's just a lot of calculation to do. The more calculation you do, it's easier to make mistake. Okay, and it's really helpful to know this proposition over here, and we're gonna use a lot. We're gonna use this formula a lot in the future. So I will encourage you to remember this proposition. All right. So the very last part is that once we know the definition and the proposition of variance, let's take a look at this proposition over here. The variance ax, or the variance of a function, the variance of a linear function, I mean, the variance of ax plus b is going to be equal to a squared times the variance of x. So basically, if we want to take the linear function outside of the variance, the coefficient part would be squared, and then the constant part would be gone. Why that happened? So let's take a look at the proof here. So we're gonna have that the variance of ax plus b. So based on the proposition we just went over, that would be equal to the e of ax plus b squared. Of course, the square here applies to ax plus b, and that minus e of ax plus b, the quantity square. In this case, the squared applies to the expected value. So what do we want to do next? So we want to spread out that square here. That is equal to e of a squared x squared plus 2abx, and then plus b squared. And then minus, so we apply the proposition of expected value. The inside of the square would be equal to a of e of x plus b squared. And then we just spread it out again. So this part would be equal to a squared e of x squared plus 2ab, since both a and b are constant numbers. 2ab e of x, and then plus b squared, because b squared is constant number, e of b squared is just b squared. That's the proposition of the expected value. And then we do the same thing here. We wanna apply the perfect square over here. It's gonna be a squared e of x squared, right? And then plus 2ab e of x, and then plus b squared. And then we're going to simplify it. Okay? So we have 2abEx and minus 2abEx over here. So those two will be canceled out. And we have b squared minus b squared over here. So these two will be canceled out. And then we're going to have a squared e of x squared minus a squared times the quantity square of e of x. Of course, in this case, a squared is constant number, so that would be a squared times e of x squared minus e of x quantity squared. What's inside? What is e of x squared minus the e of x quantity squared? That's the variance, right? So this would be equal to a squared times the variance of x. That's how we got this proposition over here. Okay. And then we know that the standard deviation is equal to the square root of variance. Let me clean this real quick. Now let's take a look at how we got this. We know that the standard sigma ax plus b, that's the standard deviation of the ax plus b, that's equal to the square root of variance ax plus b, right? And we know the variance of ax plus b is equal to the square root of a squared, the variance of x. This inside of square root is equal to the inside of square root over here, based on what we just proved. And then that would be equal to the square root of a squared times square root of variance of x. So if the square come out of the square root, it's going to be the absolute value, right? Because we want to guarantee that the square root is positive or greater than or equal to 0. So it's going to be the absolute value of a times the square root of variance of x is going to be the standard deviation of x. That's how we got this over here. Okay. So of course, if b is 0, this is going to be equal to the standard deviation of ax is going to be equal to the absolute value of a times the standard deviation of x, because if there's no constant part, we just need to apply this formula over here. If the coefficient of x over here is 1, so the coefficient of this standard deviation is going to be 1 as well. So it's going to be 1 times the standard deviation of x, which is equal to the standard deviation of x. So that it wouldn't change anything. Okay, actually, I will highly recommend you to remember this proposition we just went over here, because it's gonna save you a lot of time. So if we go back to the previous example as what we went over, we have that based on what we got over here, we know that the variance of x is equal to 3.2275, and I will give you that y is equal to 3x plus 2. So I want you to find variance of y. So what we need to do, we just need to apply this proposition. So variance of y is equal to variance of 3x plus 2. And if we want to take the linear expression outside of the variance, the coefficient part would be squared, which is 3 squared is 9. 9 variance of x. 9 times the variance of x, and then the constant number part would be gone if we take it outside of the variance. So that would be equal to 9 times the variance of x, so which is equal to 9 times 3.2275, which is 29.0475. So it's very, very easier to find out the variance of 3x plus 2 if we know this proposition over here. Alright, so once again, I will highly recommend you to remember the proposition of the expected values and the variance we just went over, because it's gonna save you a lot of time. Alright, that's pretty much all about this video.